Hi everyone, I'm Audrey. I am working in Dr. Hoefelmeyer's group this summer, and we are exploring iron oxide nanoparticles. We're synthesizing them in lab right now with the eventual hope of creating hollow iron oxide particles for uses, potential uses in solar energy, diagnostics, and drug delivery. So I am just going to talk about, these are the goals of the course, not so much my findings, because my findings kind of reflect our goals. So we are working to gain a knowledge of computational chemistry to further competitive research, in my case, of the iron oxide nanoparticles. And we're using these theories in VASP and Gaussian, and my findings are all in VASP just because sake of time and preference, I guess. And we're building a database of basic VASP and Gaussian commands, and using other tools as Vesta and BMD, and just looking at different types of iron oxide structures. So we first worked with a quantum dot which featured 16 irons and 16 oxygens. We just downloaded a unit cell right off of open crystallography database, opened it in Vesta, and with Dr. Killen's help, we created this quantum dot, sort of hoping to represent a spherical nanoparticle, which we have found in lab so far. We saw that there are partially filled spin states versus the up and down, and also there's a difference of about 68 comparing the homos, and this correlates it being very magnetic, which we found in lab with our nanoparticles. And the total energy from the file. So this is a mapping of the HOMO and the LUMO. I'm sorry that you can't really, it didn't look like this when I created it in the lab, but you can't really tell the oxygen. It correlates or oxygen from the iron, it correlates completely with this image. So this would be an iron and oxygen and iron and oxygen. And you can see, just for example, on the down spin of spin 2, the highest occupied orbital shows d orbitals. So just like looking around, you can see the different shapes and what they mean. So this is the density of states created, and as presenters before me have talked about, density of states describes the number of states per interval of energy at each energy level. We can see the difference between the upstate and the downstate spins, which is interesting moving forward, comparing this to the other model I've created. So these are some absorbance spectra. It doesn't really, it absorbs everywhere, so I'm not sure if you can see because of the light, but that's a blackish, brownish material from just Googling iron oxide, but we also found in the lab it was very, very dark particles, so that correlates to our findings. And for another kind of example, sort of to compare, we made an Fe4O4, just kind of differentiating the size, but building the unit cell. This is just a different image of building the unit cell. Similarly, it's magnetic with a difference of 16, and those are also the energy. And this one was interesting because in making the density states, we used different and up-down values, where in the previous example it was a relaxed state. So here we used n up-down equals 15, which is, the next one up would be 16, so this is right below, and then this is of 0. And further work would definitely be to see all the values in between and compare the different charts. And this is the absorbance spectra of this model, which shows absorbance kind of in the reddish or brownish, which is that picture right there. And these are the conclusions of our workshop, 2-week intensive. And yeah.
Okay, let's thank Audrey.